Well, good morning, all.
Good morning.
It's always difficult to talk about these technologies that start out by having wild optimism and it's just around the corner, and wherever year that passes, it's actually farther away. And I would classify fusion in that category. A lot of progress has been made, but I would say when I started in the 80s with a tokamak fusion test reactor, wow, 10 years, 20 years, we'll have a power plant. 30 years later, we're talking maybe in 30 years, maybe in 40, we may have a power plant. And at the rate we're going, 10 years from now, we'll be talking 50 years from then, we may have a power plant. Am I advancing this, or are you?
Yeah.
Okay, I've got it. All right. Start out with the very basics. When you split an atom or where you fuse nuclei together, the masses of the product are less than the masses of the particles that combine, and that's why you get energy release from Einstein's theory. So it seems pretty simple, okay? However, in fusion, things are not so simple as in fission, where you use neutrons, the neutral particle that can penetrate the nuclei. In fusion, the nuclei, in order to fuse, have to approach, and in order to approach, because they do carry positive charges, have large Coulomb forces that repel them. So, in principle, if you achieve fusion, it can provide an almost unlimited supply of energy, and it's benign. It's unlimited because fuel is available in abundance, as I'll explain later, and benign because it produces no long-lived nuclear products, and it's inherently safe. That's the easy part of fusion. The bad part is that the probability of two nuclei fusing together is extremely small. Part of it is, again, due to the repulsive forces that prevent the nuclei from getting together. And another part is because the cross-section, which explains the probability of the two nuclei fusing, is very, very small. And if you look here, it requires temperatures and energies to be in excess of 10 keV, which corresponds to about 100 to 200 million degrees centigrade. And right now, of all of the known possibility of fusion, which by the way is what powers the suns and the stars, and that's given us all of the elements in the universe right now, the one that relies on the deuterium-tritium reaction is the one that has by far the highest cross-section, and it's the one that is being proposed to be utilized for the fusion devices, at least in the near term. There will be other reactions that become possible once we know how to harness the power of fusion. In an eventual power plant, this would be the reaction. You use deuterium, which is available naturally in water, essentially an infinite supply, and it reasonably extracted from water. However, tritium does not occur naturally, it has to be manufactured. So initially you will have certain tritium, and then you have to breed additional tritium. The reaction of the deuterium-tritium gives rise to an alpha particle with 3.5 MeV of energy and a 14.1 MeV neutron, single neutron, which then can be used to bombard a material in a so-called blanket, which has to have neutron multipliers, otherwise you would never get breeding above unity. And this is what has been done. Materials like beryllium and lead are added to the blanket to multiply the neutrons. Some of the neutrons then go into breeding additional tritium, which again give an alpha particle of 4.8 MeV, and the remainder goes into making energy as heat. There are two basic approaches to harnessing the power of fusion. One is magnetic confinement, where plasmas of particles are fused together and confined and controlled by strong magnetic fields. And the other one is inertial confinement. Particles are made to fuse by application of external beams, right now primarily lasers, but you could also use ions. I'll start with the second because it's the one I know the least about, and so let's get that out of the way so that I can then concentrate on the one that I know the most, which is magnetic confinement. Now, in an inertial confinement, you compress and heat the target at a time that the fuel does not have time to escape. Because it's the fuel inertia that precludes the escape, that's why it's called inertial confinement. The best example of inertial confinement fusion is the hydrogen bomb, by the way, so we know it works. The net energy production from either inertial confinement or from magnetic confinement requires that the product of the particle densities that are going to be fusing together and the confinement time, the time that they stay together, exceed 10 to the 15 nuclei second per cc. This comes from a Lawson criterion which says, you know, the net energy production from fusion has to be equal to the energy that escapes, and that's defined as break even. Well, if you take that in an inertial confinement, the times of confinement are of the order of nanoseconds. That means you're talking about plasma densities that are about 10 to the 25th, 10 to the 31st. That's 300 to 400 times the density of lead. Okay? In the magnetic confinement, which confinement time are of the order of seconds, you're talking of densities that are 10 to the 15 or less, which are 1,000 times less than the density of air. So those are the two big bounding. Different approaches are being proposed for inertial confinement, so let me start with those. One of them is direct, where the beams impinges directly to target, and the other one is indirect approach, where the beam is focused on a little hole round, which then heats the target inside. Well, it is more or less in focus. When I put this slide together, the left-hand side was very focused. With my eyes, it looked focused to me. Turns out it's a little bit out of focus. But what's important is all of this big thing, and this, by the way, is the National Ignition Facility at Lawrence Livermore. All of this part that deals with the lasers is so you can deliver these lasers inside this spherical containment, if you will. And within that containment, you find that the lasers are focused, enter both ends of this little hole round. You can see that's a person's finger, where they create X-rays. It's ultraviolet light creating X-rays. The X-rays ablate the surface of this deuterium-tritium grain of rice, if you will, and think about it as a rocket. The ablation causes like a rocket, and the force from the rocket compresses the target so that it exceeds the density at its core, it ignites, and then the fusion reactor propagates out. Or so the theory goes. NIF has been built. The lasers are working. They have not succeeded yet in focusing all of the lasers and creating the X-rays so that the X-rays hit the target symmetrically so that the target doesn't move. If there is no symmetry, instead of creating a compression, you move the target. Okay, so all expectations are that we will succeed. However, think about now what would happen to create a power plant from this concept. And by the way, the United States aren't the only ones that are pursuing inertial confinement. There is a similar facility near Bordeaux, France, called the Laser Megajoule Facility. The NIF uses 192 beam of neodymium lasers. They group them, and then they focus them. The neodymium lasers produces light, not in the ultraviolet, so you have to pass it through certain crystals to convert it to ultraviolet. Same thing at the Bordeaux. Bordeaux uses a larger number of beams, but the concept is essentially the same. And then throughout the world, I don't know why I'm having problems. Okay, maybe I need to push this in that direction. This is some of the examples of where other countries are pursuing inertial confinement. And beside these large facilities, there is also smaller facilities that have been in operation for a longer time. The smaller facilities enable you to study the physics of it, but they don't permit you to get to the state where you can get the right compression and so get the result that you expect. Now, Lawrence Livermore has also produced a conceptual study. I give up. There we go. Which they call LIFE, which is an integrated approach to plant design. It looks fine, like Recover used to say. All concepts are simple, they're not expensive, there's no problem in resolving the issues. Then real reactors are a little different, okay? They cost more, they take longer, and there's a lot of difficulties. Think of the problem. Right now, the scientists have to manually insert the grain of rice in the hole round, has to be precisely centered in the center of this sphere. Okay, think about doing this 20 times per second, shooting the whole round and the grain of rice as a bullet, and have that done continuously and reliably so that this plant produces power on a continuous basis. That's the difficulty of the inertial confinement. Now, are there difficulties that can be overcome? Of course. Man is very ingenious, but there's an awful lot of R&D that has to be done, even after you learn the physics. Now, for a long time I used to think, well, surely the path forward is magnetic confinement because inertial confinement is way too complicated. Well, as I will show you, magnetic confinement isn't that much simpler either, and it's got its own set of problems. Magnetic confinement is different approaches. By the way, it's good that we're pursuing both approaches because the physics is similar, but it's also different. So if we end up in a problem area in one of them, it's good to have an alternative. Within magnetic confinement, basically there's two fundamental concepts that are being pursued. And one of it is the tokamak concept, where plasma is confined in a torus, and it's confined by the interaction of a toroidal magnetic field with a current that is generated by a central solenoid, and the interaction of the magnetic field generated by the current with the toroidal field gives the right confinement, the right magnetic bottle within which, and I'm oversimplifying it because there's lots of other problems. And then the stellarators, where the actual magnetic field is created by a shaped magnetic field by specially designed magnets. And I will show some examples. Now, as I say, this is very, very simple because in addition to confining the plasma, you have to control it, and there are instability, there are disruptions, and we're learning how to control those better, but we're not quite there yet. So there's an awful lot yet to be learned, and more importantly, we have not operated in the regime that a power plant would ultimately wish to operate at, which is the regime where the fusion reactor becomes self-sustaining, meaning that the heat that is generated by the alpha particle alone created by the deuterium-tritium reaction is what keeps the reaction going. It becomes then self-sustaining. Right now, we have to use additional heat outside to get to that regime, and then maybe we'll learn. Now, we know that fusion works. I'm sorry, going back. Okay. It doesn't really want to go back, does it?
You're hitting,
No,
hit the right arrow or the left arrow.
okay.
Yeah.
There you go. There have been two devices worldwide that have operated with tritium. One of them was the tokamak fusion test reactor that I helped design, and the other one is a joint European torus in Culham, England. The jet produced 16 megawatt of fusion power. TFTR produced 10 megawatts. So we know we can make it work. The real question is, can we make it work reliably and on a scale that is necessary for a power plant? And that's where I'm going to spend the rest of the time. And I'm also going to try and connect that to Richard Denning's talk. Okay. It's fusion is characterized as having pretty much worldwide cooperation amongst all of the countries that are pursuing. And that's true both of the inertial confinement as well as magnetic confinement. This is just a list of the major fusion research reactor. To just paraphrase that, every tokamak looks like any other tokamak, but they're all different. I'll give you a very quick set of slides that give you the various devices that are present in various countries. In the United States, we have the National Spherical Tokamak Experiment, which was built in the 2000 time frame. TFTR has since been decommissioned. At the Massachusetts Institute of Technology is Alcator-C mod. At General Atomics is AA3D. And then Prisma Plasma Physics started building a national stellarator, changed their name, but that work has been suspended. And so we got pieces of the machine sitting there. But China is interested in possibly acquiring it and finishing it. There have been other designs that have eventually were exported to other countries like Korea, where a Princeton plasma physics design became K-STAR in Korea. Japan had JT60, and that has since been stopped, and they're now proceeding with the JT60 upgrade, which will be a superconducting machine. As you can see, they're all tokamaks. By the way, a spherical tokamak is one which is fat. The minor axis, the axis of the radius of the torus, is large compared to the major axis, which is the distance from the center line of the machine to the center of the torus. And there's certain advantages to that. And then a conventional tokamak typically has a minor radius to major radius ratio of about major radius to minor radius of 3. Korea used a design I was involved with, which was the next physics experiments, the Sprintum. It was stopped. Korea converted that to a superconducting tokamak. K-STAR, which is now starting operation but has not yet achieved its major parameters. China has eased, and I couldn't get a picture of these for you. This is why a stellarator looks more complicated. You know, the toroidal field coils in the tokamak are D-shaped or circular, depending how you design your tokamak, but they're straight. These are the toroidal field coils. They are twist and turn, and different stellarators have different modes. Sometimes they have 3 different nodes, like the Wildenstein accelerator in Germany, which is being completed and now starting operation. This is a picture of Wildenstein as it's being constructed. So a stellarator is much more complicated physically to design and construct. It has an advantage. It doesn't rely on the transformer from the central solenoid to generate a current in the plasma, which by definition makes a tokamak a pulse machine, however long the pulse is. A stellarator can operate at steady state. So there's the supporters of stellarators and the supporters of the tokamaks. Russian facilities. Russian, by the way, were the inventors of the tokamak, and even now it's seen as being the path toward really getting to self-sustained fusion, because it's the simplest of these machines. Now, there's 3 points I'm going to make out of these slides. The way in which people follow the progress of fusion is by the triple product of energy, confinement time, density, and temperature, which is plotted on the ordinate, versus the central ion temperature of the nuclear that collide. Bottom line, the point that I want to make is, since the late 2000s, there has not been a machine put in service that enables us to explore the region of reactor conditions, which is where self-sustained, or even something approaching that. In particular, the United States hasn't had a new machine since the late 2000s, and that machine cannot get us there. So that's problem number 1. The second issue has the fact that, related to the first issue, the fusion hasn't really been supported financially by the various countries. Despite countries continuing, the support hasn't been so heavy as permitting the progress that we would like to make. And then third is that we have learned enough that we know where we need to go in order to get to self-ignited fusion, self-sustaining fusion. And all of these experiments that have been done to date help support us. Now, the final point I'd like to make is that just as China East is coming online, K-STAR is coming online, Wildenstein is coming online, those machines are capable of getting into the regime that approaches the self-sustained fusion. But it's the next step that's going to get there, and that's what it's the one that they refer to. Used to be called International Thermonuclear Experimental Reactor. That's a mouthful to say, so now it's just called ITER. And ITER is also a Latin word for the way, and as I paraphrase it, the way it's going, it probably should be not the way, because it's got a lot of problems. Now, why is fusion taking so long? Why this great optimism up front for both inertial confinement and magnetic confinement? Well, first of all, you're talking about heating volumes of gas, plasmas, to millions of degrees centigrade without touching the wall. The moment it touches the wall, beside damages to the wall, the plasma extinguishes itself. So you're done. You have to achieve it for a long, long time, and you have to achieve it reliable. We have to achieve 500 million degrees for a few seconds, and we've only achieved maybe 10 million degrees for minutes. So we're a long ways yet from where we need to be. The materials, both from inertial confinement as well as from magnetic confinement, are not yet to where they ought to be. We have to develop robust material for the walls to be able to withstand the nuclear bombardment and the heat loads. That's underway, but a lot more work needs to be done. And then we have to ensure that it can be made into a power plant. I mean, it's got to operate continuously and reliably for a long time, and we are very far away from that. Think about it. NIF, manually inserting, one shot every, maybe few days, versus every 20 for every second, and then continuously. The other problem is that all of the scaling law that we have learned today from the experiment tend to tell us that we need to get progressively larger device, because the power output scales as the square of the size of the machine. That means to get to where we want, we have to be bigger, it's going to cost more, it's going to take longer. And again, it's not funded with any sense of urgency. So what's the next step? This is roughly to scale, but not. The only scaling is demand. So compare demand for jet versus the jet machine. Outwardly, they appear the same, versus demand standing next to ITER, which is presently being built in Cadarache, France. It's a gigantic, I call it Swiss watch, because everything has to work just perfectly in order for this machine to perform. We need to build this much larger machine, ITER, and it is being built. The design is virtually complete. Now, design started in the 90s. Here we are in close to the mid-2010s, 2013, and the design is not yet complete, and we just started construction. ITER will demonstrate both the scientific and technological feasibility of fusion power. It is an international project with the pluses of an international project, but many of the minuses. It involves 7 parties: China, the European Union, which in itself is not a single entity. It's run by Brussels, but fundamentally it's many, many different countries, Europe, each with their own ideas. India, Japan, Russia, South Korea, and the United States. There is an ITER organization based in Cadarache, France. The ITER organization is responsible for some of the design of some of the components, and it's also responsible for the overall integration. But the actual components come from the domestic agencies as contribution in kinds. So no matter how much it's going to cost you, you're going to contribute that component or pieces of that component for a stipulated amount or credit that you get. Now the telltale sign is that the ITER director, which reports to a council of the various parties, formed by various parties, does not have direct sway over the domestic agencies. Domestic agencies don't report to the director. So for any of you who've been in management of the project, that tells you something. The people that are actually doing the production don't report to the project manager. Not surprising, the project is not exactly running very smoothly. There has been significant delay in the schedule. There has been significant cost increases. Now, indeed, ITER is a truly dramatic step, okay? First of all, it sits on an acreage, 103 acres, that you can put several nuclear power plants on. It has 39 buildings. The main one is this one. This is, the tokamak actually sits here. All the other buildings are to support that tokamak, the power conversions and so forth. Where are we with the construction? Okay. It was sited in Cadarache because that's where the Commission Énergie Atomique of France does all of their research reactors. It is a high seismic. It's on a fault, the Durance, the River Durance fault. Therefore, the actual device sits on seismic isolators. The seismic isolators are all in. The slab upon which the cryostat and then the tokamak inside the cryostat will be found, because this is all superconducting, is not being poured yet. The rebar for the slab is in. This happens to also be the first fusion reactor which is going to be regulated by a nuclear regulator. Therefore, it has to have its own safety analysis report, and it has to answer to the regulators. It's the first time. And one of the first things that happens is, do the project have the right nuclear safety? Do the project people have that in mind? Because the regulator can stop you at any time. As a matter of fact, right now they have questions, have you got enough rebar on this slab? You thin that slab. Are you sure that it's safe enough? Even though it's inherently safe, they are handling as if it were a nuclear power plant. Now, the regulator has got his own set of problems. This is the first time they ever licensed a fusion reactor. So for them, it's also new. That also. Now, the good news is in 2 years, the project has received permission to construct. In 2 years. Let me go back. This is a different plot of the same triple product. But the bottom line is that all of these experiments, even though they didn't allow us to get to where we want with the self-ignited fusion, they did provide the knowledge that says, here's what ought to happen when we get there. And ITER is built on all of these experiments, and ITER will be the first to truly provide the ability to do physics of burning plasma. Plasma that is heated by the alpha particles. Now, you can be a pessimist and say, my God, who knows what's going to happen? It's going to be bad. Or you can be an optimist, and I choose the latter. When we get there, we may find that the physics of when the plasmas are heated by other particles is a lot more benign than we think. And we will learn. That's the great hope. We haven't been there long enough to know. So we must take this step. Because people say, the power plant isn't going to look like this. Why should you bother with ITER? Because we need to know what happens when you are in a self-sustaining plasma. We simply do not know. ITER alone will produce more power than any other experiments all combined. So you're talking about producing 500 megawatt of power. Now, to produce that, we have to have 73 megawatt of external heating, neutral beams, and then resonance heating, either ion or electron or hybrid resonant frequency that is used to both drive the current and also heat the plasma and keep it heated. So things are not very simple. I mean, when I said you have a toroidal field and you have an interaction with this current in the tokamak, for instance. Yes, but then also you need additional coil to control and shape the plasma, colloidal field coils. You may need internal coils to prevent disruptions from really destroying your vessel. So as you learn more how to control the plasma, the more complicated the machines become. Now, when can we expect a commercial nuclear power plant? Okay, ITER is now probably 10 years away from completing construction. Completing construction means we will run a set of experiments without introducing tritium. Maybe in another 10 years we'll introduce tritium. Meanwhile, we'll have to operate a minimum of another 3 years to really learn what happens from ITER. So you're talking learning from ITER maybe 20 years or so, perhaps more if it gets further delayed. We need to understand more how the materials work. There is a parallel effort to ITER supported by Japan and the European Union, where they are going to design and build an international fusion material irradiation facility in Rokasho or Naka, Japan. There is also an international center for science located in Naka. And as part of this broader approach, as they call it, Japan is upgrading JT60 to make it superconducting. Need further development of the technologies, how to do the power conversion, because part of ITER is, okay, the breathing blanket eventually will be needed. So there will be ports in ITER where different parties put in experimental portions of the breathing blanket, different concept of the breathing blanket, and right now everyone's calculating about 1.08 as the breathing cycle. And then you need to work on the design of the demo. Some parties have already started, but to start building a demo, you're talking 20 years plus for sure. And then power to the grid from the demo would probably be in 30 years. So we're talking 30 years, and my feeling it's probably going to be longer. And so we're not talking about commercial fusion until the second half of this century at best. Now, what is the cost of fusion? Because it's got to compete with the other supplies. Well, there have been studies made. The ARI studies in the US said, well, we could build, for about $5 billion. And that would be about 70 cents per kilowatt hour. Okay, that's fine. Europeans have done a similar study, both with advanced material and not advanced material. You can read that for yourself. But you can also come up with costs that range between 10 and 17.5 cents per kilowatt hours. And my question is, are those costs believable? And I have some doubts. Okay? The economics favors large power plants. So what you will find, if I try to plot, see fusion, I use those costs in terms of the range. So it shows competitive with nuclear, it shows competitive with other forms. So it should find its place, particularly near large population center and where you need large amount, because fusion by nature will require large power plants. Problem is, how confident are you? I'm certainly not very confident. I'm looking at ARIES. ARIES is 1,800 megawatts of thermal power at 5 billion. ITER is 500 megawatt, and it's north of 15 billion. North. Okay, what are we going to do? Do we really expect a tenth of a kind or so to be a factor of 3 less than what we're experiencing today? Now, granted, part of the cost of ITER and all that is because of the international nature, because of the way they set up the agreement between the parties. So some of that can be done. But there's an awful lot of assumptions that have been made in these studies that are questionable. In order to generate those costs per kilowatt hour, you have to assume a certain capacity factor and a certain availability. Now, imagine what could happen to ITER if one of the toroidal magnets doesn't work. It's going to be years disassembling the machine and putting it back together. Okay? I've talked about inertial confinement. How long is it going to take before you figure out how to shoot those bullets reliably? And what happens if you can never get there? Now, which utility would order such a device? Okay? So there's some real question. Now, are there showstoppers? Well, on paper, no. On paper, no. But as I said, there's an awful lot of research and development that needs to be done to take us from, I call, feasibility of a power plant to a real power plant. If I sound negative, trust me, I'm a supporter of fusion. You should hear the detractors. Now, why do we need it? Well, I intentionally made these slides very, very general because, like any projections, there's a lot of uncertainty. But the fact is, the world needs energy. Richard has made a pretty eloquent talk about why you need energy. And if fusion is so complicated, why bother? Why not use other sources? Well, the answer is pretty simple. And he's kind of told you. Some of the sources are not inexhaustible. Some of the sources, like renewables, are not easily usable. He referred to some of the problems. And a person asked a question about land use. There's lots of issues with all of the other. Point is, a right approach says you should employ a combination of all of the sources, not just focus on one or the other. This, to me, is the answer why fusion. If we are successful, and I truly believe we will be, certainly not in my lifetime, but we will be successful. This is a slide that I copied from Chris Llewellyn-Smith, Professor Smith. And he was the past director at CERN, at Cullum in England, and he was the first chairman of the Council for ITER. You look at this, and the lithium from one laptop battery with 40 liters of water gives you the per capita consumption for 15 years. I mean, this is the promise of fusion. This is why it's worth pursuing. If successful, we will then stop worrying about being able to get electricity supply. Now, I also paraphrase, remember what Kennedy said about the moon? Of course it's difficult, and that's why we want to do it. We want to do it because fusion is difficult and because of the benefit that mankind can accrue. This is what I'm going to try to tie it to Dr. Denning's talk. Whether we call it security, independence, whatever, we need to pursue all of the options. Electricity can displace many of the other options. He talked about 800 plants. I quickly looked at, if we wanted to go full electric propulsion in the United States, displace every gasoline or diesel engine that we have on the surface, 100 gigawatt of new power plants would enable us to do that in about 15 years. It would revolutionize the way we do things in the United States. Detroit will clearly be different. You know, there'd be no gasoline engine production anymore, it's all electric. Because of our large distances, we couldn't just do plug. We would require gas station to become battery station, where you exchange batteries, you know, on the fly. The technology already exists. The Israelis do it. You eliminate the dependence on foreign oil. I know we're reducing it, but we're still paying $300 billion that leaves our shores on a yearly basis. That's $300 billion. So, I mean, if you have significant electricity production, you can do a lot of things that we right now don't even imagine, solve a lot of the problem. Renewables would be augmented, because if you'd start having distributed battery throughout the country, you now have the storage system that you can use for renewable. You know, it's not a joke, it's truism. In Finland, there's a nuclear plant, and right next to the nuclear plant there is a windmill. And they build a windmill, and they ask the operator, why do you have that? It's to answer the question. And every time I'm asked that question, the answer is the same. He says, why do you have the windmill? He says, because it would take 1,000 of these to do what this plant does, and then we would have to play for wind. And so, all of this says we need alternate form. Now, is fusion the near term? Obviously not, but what I've told you. But it is the longer term. Fission can carry us a long ways. And there are concepts of reactor that I'm sure you're all familiar with that can be made as nearly inherently safe as you can, so you don't have the issue of land being destroyed. So there's things you can do with fission. But fission is not an exhaustible either. You cannot continuously breed forever. No, it can go on for hundreds and hundreds of years. I can grant you that. But I think fusion needs to find its place as well. So, what was the early promise? Oh, the early promise was great. I mean, I remember people coming, my old company, with concept for fusion reactor. Fusion, not in a bottle necessarily, but, you know, I can design this tokamak that'll work perfect from day one, okay? It was just around the corner. Turned out to be a corner with a very long radius. Reality has told us otherwise. It's sobering, unfortunately, but we shouldn't give up. Lots of progress has been made. We understand a lot better what it takes to make a fusion reactor work. That has formidable obstacles. If you were to ask me, is it possible to make a fusion power plant? My answer is resounding yes. I have no idea what it'll look like. I strongly suspect it'll bear some similarity to, if it's magnetic, to a tokamak, but it won't be the same tokamaks that we're designing today, because we will learn when we get into the self-ignited plasma that things are different and we can design things differently. But I am very certain that we must pursue fusion as I wouldn't call it an alternate, but a complementary to what fission can do for us. And there are very few large scale, low carbon alternatives, and this is one of them. So let me conclude with that and